what is the state of stress a soil experiences in situ? We're going to make several assumptions in this case. We are going to assume that it is level ground and that it is either saturated or perfectly dry, so it is not an issue of capillary and suction, capillary effects and suction altering the state of stress. So we need to recognize that there are two extreme conditions, because contrary to a solid, where I can apply huge stress, infinite stress anisotropy, I'm applying a very high load on this pen. However, I have zero lateral stress, so my stress anisotropy is infinite. However, a soil cannot accept infinite stress anisotropy because the strength is frictional. And so let's review some of those concepts, and for this video, remembering some of the analysis we did with Mohr circle and Coulomb failure envelope will prove to be very useful. So let's take one extreme, and that extreme is the case where the lateral stress is being relaxed because the crust, the sediment, is being pulled apart, is experiencing extension. If this is the case, the soil, which started with some initial state of stress, this is sigma z and this is sigma horizontal. The horizontal stress is getting smaller and smaller and smaller until it touches the failure envelope, and this is the minimum horizontal stress that the soil can take to resist that sigma z. Let's go to that extreme case and analyze what the conditions are. We erase the initial circle for clarity, but please recognize that, and this is very important, that these are all effective stresses, because this is what the skeleton feels. So if the system is below the water table, it doesn't matter. This is truly effective stress. And so let's call the distance to the center of the circle c and the radius r. So now we can say that sigma horizontal effective over sigma vertical effective, and this is the minimum, the lowest sigma horizontal can get, is equal to the center minus the radius over the center plus the radius. Center plus a radius is sigma z, center minus a radius is sigma h. Dividing numerator and denominator by c, I get that this is 1 minus r over c over 1 plus r over c. Now, if you look at r, I can also draw it here. And if you see this triangle, where this is the friction angle, then this is opposite over hypotenuse, so this is sine phi. And this is the one extreme of a stress anisotropy a soil can take, where we have done it by decreasing the horizontal stress. This is what would lead to, in geotechnical engineering, what we call K-active. In geology, where we are stretching, this would be leading to normal faulting. It's exactly the same analysis and mechanism. Now, the other thing is to recognize that if this is the specimen, sigma vertical is acting on the horizontal surface. So if I draw a line parallel to the surface sigma z is acting on, from the point that defines sigma z, I obtain the origin of planes. And now the question is, what is the angle of the failure plane, or what is the angle where I can find the stresses at failure, which is this value here, beta. And so it gets a little bit trickier, but let's do it. We're going to draw that circle again. I'm going to erase the intermediate values. And so we are trying to figure out what beta is. And please notice that from this original triangle, if this is phi, this is 90 minus phi. And because of one of the rules about circles, the line that connects the a point along the perimeter from two diametrically opposite points is half the angle from the one to the center, so this will be 45 minus phi over 2. Now beta, if you look at this other triangle, given another property of circles that this is going to be a normal angle, then this beta is going to be equal to 45 plus phi over 2. So this is one extreme, what we call the active condition or the normal faulting condition. Let's move to the other extreme. In this other extreme now, the soil is being squeezed laterally. So if this is the specimen, the horizontal stress grows while the sigma vertical remains small, and so it gets to a point that the horizontal stress is much greater than the vertical stress. So let's say that this is sigma z effective, and this is the maximum sigma horizontal effective that we could mobilize when we touch the failure envelope. So this is once again limiting anisotropy, but now sigma h is greater than sigma z. So if we do sigma h effective over sigma z effective maximum, is going to be center plus radius over center minus radius, which is sigma h, the center plus the radius, and sigma z, the center minus the radius. And following the same logic, this becomes 1 plus sine phi over 1 minus sine phi. And please notice that this is the inverse of that expression. This is what in geotechnical engineering we call K passive, and in geology would be equivalent to reverse faulting condition. So let's add K active here. By definition. If we draw through a line parallel to sigma z, a line parallel to the face that sigma z is acting, we conclude that this is the origin of planes. So the direction to the state of stress that experiences failure is this one. So now I'm looking for this beta angle, and this beta angle, we follow a similar situation, is related to this angle, but if this is phi, this is 90 minus phi, and this is half of that, so it's going to be 45 minus phi over 2. So these are the two extreme cases of stress anisotropy in the subsurface. And now the question is, what happens in between? And what happens in between is tricky because we don't have extreme conditions from mechanics, and so we're going to rely more on empirical equations. And so in this regime, we are in the empirical range. But now, while this element was experiencing vertical contraction, this one was experiencing lateral compaction, and now we are going to go into another condition which is in between, where there is epsilon horizontal is equal to 0. 0 lateral strain loading, and this is typical when we have a soil that keeps getting buried and buried. The element here, it will get shorter, but it cannot get wider because all the neighboring elements are trying to do the same thing. Instead, the horizontal stress will increase. And now, how will the horizontal stress will increase? Well, it will be somewhere between these two regimes. So let's draw these two regimes. This is sigma horizontal effective, and this is sigma vertical effective. One regime is when the horizontal stress is small compared to sigma z, which is the active case, is here. And the other case is when the horizontal stress is much greater than the vertical one, which is here. So this is K passive, this is K active, and our soil now is somewhere in between. And for this one, we are going to use an empirical equation, which is called Jackie's equation. And this equation says that this K0 lateral strain, K naught, is approximately 1 minus sine phi. By the way, if you go back to Jackie's original data, there is a cloud of points, and probably you could have chosen 0.45 for all soils that he had. But this one is interesting because when the friction angle goes to 0, that means that you have something that behaves like a liquid, and in a liquid the vertical and the horizontal stress are the same according to Pascal, so it has a nice asymptote. But that's it. There was no more evidence than that. And so it appears that this is, imagine that if the friction angle is 30 degrees, this is 0.5. By the way, if the friction angle is 30 degrees, this is 1.5 divided 0.5, this is 3. So this ratio becomes 3. This one is the inverse of that, so is 0.5 over 1.5, which is 0.333. And this one is 0.5, so this one is going to come somewhere here, let's say K naught. Now you may be anticipating something that is very important. What happens if all of a sudden erosion takes place and these layers get removed? Or I do a very significant excavation and I remove all these layers, so I will unload the vertical stress. The vertical stress goes up, but that horizontal stress, good part of it gets locked in. And so when I unload the soil from burial, this will go something like that. This is unloading at 0 lateral strain. And so some of the horizontal stress gets initially locked in. Eventually, we're beginning to approach K passive. In other words, the horizontal stress can become so much larger than the vertical stress that we're actually failing the soil laterally and uplifting it. And so for this case, we need another expression. Let's say that this is sigma z prime max. And if we go to some stress here, which is the sigma z prime current, and we would like to know what is the stress ratio at that point. Well, once again, we're going to fall back onto empirical equations, and I go to a classical work by Main and Kalhawi. And so there are different equations because it all depends where you are on the unloading path and whether you are reloading. But let me give you one that is easy to remember. The K naught for a soil that has been preloaded is going to be approximately the K naught of the soil that has not been preloaded, which is this one. This one was not preloaded, times the preload ratio, which is sigma z max over sigma z current to the sine phi. So let me give you an example. Let's say that the preload ratio is equal to 4 and the friction angle is equal to 30. So in this case, K naught is 1 minus non-preloaded, 1 minus sine phi. This is 0.5. The preload ratio is 4 and is raised to a power of 0.5. So this becomes 2 times 0.5. This is equal to 1. So a preloaded soil with only a preload ratio of 4 may experience a horizontal stress equal to the vertical stress. And if I continue preloading, I am beginning to approach the K passive regime. So actually the horizontal stress may be higher than the vertical stress. And this will affect from subsequent settlement to the stiffness that I measure with shear wave velocity, etc. So this was a simple example, but if the friction angle was approximately 40, don't think that this changes much. This becomes that you need a preload ratio of approximately 5 for stress reversal. So somewhere between 4 and 5, if I continue unloading, I'm going to have a stress reversal. In other words, the soil now moves into a regime where the horizontal stress becomes larger than the vertical stress, where this is the 1-to-1 line. That will be K equal to 1. Now, you may wonder, how come the non-preloaded K naught is approximately 0.4, 0.5, and from a granular material point of view, you can think of a simple example. And so let me use this empty corner here to make you a sketch, and to leave it as an assignment. And imagine that the soil is in this form of packing, and now I apply at the top a vertical load of 1, and so you see this particle is pushing these two particles to open up. So, and the same this one, so it's wedging between the two. So for the system to remain in equilibrium, I will have to resist with a certain force if I want to impose a zero lateral strain condition. And from this pure geometric condition, you can begin anticipating what will be the lateral stress I need to apply to resist that vertical stress. Also notice that there are fabric assumptions being made here. If instead of this fabric I would have used a simple cubic packing, an idealized geometry that never happens in nature, but if I would have, then all the vertical stress is totally taken by the subsequent grains, and I need only a virtual force almost zero to keep that from buckling. But really that is too idealized as an extreme condition, so this is a better analysis to explain K0 that has not been preloaded.